Hello everyone. The title of this video is Using the Linear Factorization Theorem to Find Polynomials with Given Zeros. So in this video, the examples I'm going to do are taken directly from a free online textbook at openstax.org. I'm in their Algebra and Trigonometry text, section 5.5 called Zeros of Polynomial Functions, and I'm under the heading Using the Linear Factorization Theorem to Find Polynomials with Given Zeros. So each example I'm going to do is either going to be an example taken directly from the reading, or one of the try it problems from the reading, or one of the exercises at the end of the section that's related to this particular objective. Okay, so first I'll talk about what are the theorems, what are the important points of this part of this section. So here they have, the linear factorization theorem tells us that a polynomial function will have the same number of factors as its degree, and that each factor will be in the form x minus c, where c is a complex number. In fact, we saw this in the last video on fundamental theorem of algebra. Right, that showed up here, where you can write a polynomial as its lead coefficient, a, times x minus c1, x minus c2, all the way to x minus cn, where each of these c's is just one of the complex zeros of the polynomial. And a degree n polynomial will have n complex zeros. So that's really just the same thing as that. Now, the important part we need to remember, the important thing we're going to use here is really the complex conjugate theorem. All right. So this is huge, right? Pay attention to this one. If the polynomial function f has real coefficients, all right, real coefficients. So no we haven't come across any imaginary coefficients for polynomials terms yet, and we're not gonna. So this will apply to like basically every polynomial we see. So if the polynomial function has real coefficients and a complex zero in the form a plus bi, right, remember I is that square root of -1, right, the imaginary unit, then the complex conjugate of the zero, a minus bi, is also a zero. Alright, so what do I mean by that? So, for example, if f of x is a polynomial with real coefficients, and real coefficients, no imaginaries, and say x equals 2 plus 3i is a 0, then its conjugate, x equals 2 minus 3i, is also going to be a 0. That's an example of the complex conjugate theorem. Alright, and we're going to use this. So basically, if you have a polynomial with real coefficients, the zeros that have an imaginary part to it come in pairs. So if you have a polynomial with real coefficients, you're never going to have an odd number of imaginary zeros. You can't have just one or just three. They always come in pairs, conjugate pairs, like that. All right, so the examples I want to do now, the examples we're going to do here in this video, we'll be given some information about a polynomial, and then we'll be asked to write an equation, write a formula for that function. Now, I have done this in previous videos before, but in those videos, all the zeros we were given were real. Right? There were no zeros with an imaginary part like these two. That's the only major difference. Right. So let's start. I want to do example 7 from the text first. Let's take a look at that. So here they're asking us to find a 4th degree polynomial with real coefficients that has zeros of -3, 2, and I, such that f of -2 is 100. Now the only reason they're giving us this last part is so we can find the lead coefficient. All right, we know the zeros. This last piece of information is going to help us find the value of that a, right, the lead coefficient. All right, so I'll write this stuff out. I'll write out this information. Right? So we're told that its degree needs to be 4. Right? It's a 4th degree polynomial. We're also told that it has, real coefficients. It has to have real coefficients. And since it has real coefficients, the complex conjugate theorem will apply. Now the zeros are, they told us x equals -3 is a 0, x equals 2 is a 0, and x equals I, right, the imaginary. Oh, wait a minute, right? If it's degree 4, it should have 4, including multiplicities when you count with multiplicities as well, but it should have 4 complex zeros. I'm only seeing 3. But this is where the complex conjugate theorem comes in. Any 0 with an imaginary part is going to have a counterpart, something that's also a 0. Right, because it has real coefficients, they're telling us, by the complex conjugate theorem, x equals, the conjugate of I. Now remember, I is 0 plus I, if you write it in the standard form for a complex number. So the conjugate would be 0 minus I, which would be -I, is also a 0. All right. Okay. All right, because again, that's the conjugate of I, right? 0 plus I, 0 minus I. So now I have what I need, right? If it's degree 4, it should have 4 complex zeros, which I now have. All right, so the polynomial function, I'm going to start writing an equation for it over here. Should look like this, f of x or y equals. Now there's some lead coefficient that I don't know, so I'm just calling that a times all these factors, where each factor is just x minus one of the zeros. So x minus -3, which would be x plus 3, times x minus 2, times x minus I, finally times x minus -I, which would be x plus I. All right, now I just need to find a. All right, now I just need to find a. Honestly though, first I'm going to multiply these 4 out, and then we'll find a. All right, so if I multiply these two, x minus I times x plus I, that's going to be x squared minus I squared. But remember, I squared is -1. So this is minus -1 or plus 1. So what I have here is a times x plus 3 times x minus 2, and then the 2 with the I really only wanted to get rid of the i's, so I multiply these two with the conjugate zeros here. When you multiply these two, you end up with x squared plus 1. Okay, now there's no more I, and I'll find A. Right, now to find A, to find that lead coefficient, we'll use that last piece of information that was given to us. We know that f of negative 2 is equal to 100. Alright, so that means I replace x with negative 2 and f of x with 100. So over here, there'll be 100 on the left side equals, and then a times negative 2 plus 3 times negative 2 minus 2 times negative 2 squared plus 1. Right, again, that's the reason I got rid of the I. I didn't want I in there anymore. So this is 1 times negative 4, and 4 plus 1 is 5. That's negative 20a. So the value of a must be negative 5, right, dividing by negative 20. And so we finally get our polynomial, right, in factored form. Right, so replacing a with negative 5, we have finally f of x equals negative 5 times x plus 3 times x minus 2 times x squared plus 1, right, the x minus I times x plus I. And now let's multiply it all out. All right. If I multiply these two, we get negative 5 times x plus 3 times x minus 2 would be x squared plus 3x minus 2x would be plus x, and then minus 6 times x squared plus 1. And now I'll multiply these two. And again, I hope you remember how to multiply polynomials. You distribute the x squared, take all the terms from one, distribute to the other. So I'll take these x squared and 1 here. Now if I distribute the x squared, that'll give me x to the 4th plus x cubed minus 6x squared. And then I distribute the 1, giving me x squared plus x minus 6. And then combining like terms, we get the following. So we have negative 5 times x to the 4th plus x cubed, and then minus 5x squared plus x minus 6. And then finally I distribute this negative 5, and we get our degree 4 polynomial with real coefficients that have all those zeros, and the value of f at negative 2 is 100. So it'll be negative 5 x to the 4th minus 5x cubed plus 25x squared minus 5x plus 30. And there we go. Alright, and we can double check. You can go to the graph. I'm not going to do this, so I'll leave it to you. You can go to that Desmos website, desmos.com, free online graphing calculator. Put this in. You'll see it crosses the x-axis at negative 3 and 2, right, the real zeros. You won't see the imaginary zeros, though. And if you plot the point, negative 2, 100, it'll be on the graph, right? If x were negative 2, the output should be 100 in this particular expression. Right, but that's it. I mean, that's really it. We're going to know a bunch of zeros. So x minus each of those numbers is going to be a factor. And then we'll be given some information about another point on the graph so we can find the lead coefficient. Right. And just remember this complex conjugate theorem, right? If you have a polynomial with real coefficients and any of the zeros have an imaginary part, the conjugate will also be a 0. Alright, so let's do that one more time. I just got a couple of examples, pretty short one today. So this one I want to do the try it problem number 5 from the text. Just scrolling down a little further, here's try it number 5. So here, find a third degree polynomial with real coefficients that has zeros of 5 and negative 2i. Well, wait a minute, right? If it's degree 3, it's got to have 3 complex zeros. I'm only seeing 2. But one of them has an imaginary number in it. And the coefficients they said were real, so we can apply that complex conjugate theorem, and say, hey, the conjugate of negative 2i should also be a 0, which would be positive 2i. And f of 1 is 10. Alright, so we have degree 3 with real coefficients. Then the zeros are x equals 5, negative 2i, and then the conjugate of negative 2i, positive 2i. That's 0 minus 2i, 0 plus 2i. All right, and again, the only reason we can apply that is because they said that the polynomial has real coefficients. And we know that f of 1 must be 10. All right. Okay, so we have f of x equals some number a that I don't know yet, times the three factors for this degree 3, x minus 5, times x minus negative 2i, which would be x plus 2i, times x minus 2i. And just like last time, these factors with the complex conjugate zeros, I'm going to multiply these first, just to get rid of the i's. So we have a times x minus 5. And then when you multiply these two out, and just remember that I squared is negative 1, this will end up being x squared plus 4. Alright, and you know what? Might as well finish these off here, and then we'll find a. I'll have x cubed minus 5x squared doing the inners, then plus 4x doing the outers, and then minus 20. So there's your degree 3. Now I just need to find the lead coefficient, this a that I need to distribute, and that's where this comes in. Right, f of 1 is 10, so we'd have 10 equals a times the quantity, 1 cubed minus 5 times 1 squared plus 4 times 1 minus 20. That's 1 minus 5 is negative 4, plus 4 is 0, minus 20 is negative 20. So we have negative 20a, so the value of a must be negative 1/2, dividing both sides by negative 20. So putting that all together, our polynomial function is negative 1/2 times the quantity, x cubed minus 5x squared plus 4x minus 20, and then distributing the negative 1/2 gives me the following. Negative 1/2 x cubed plus 5/2 x squared minus 2x, and then plus 10. And there we go. There's a degree 3 polynomial with real coefficients, right? All the coefficients are real numbers. And 5 would be a 0, negative 2i would be a 0, 2i would be a 0. And you can go ahead and check that. Plug in 5 for x, plug in negative 2i for x, and 2i for x, and you'll see you get an output of 0 after simplifying. You just have to hope, I'm hoping you remember how to simplify your powers of I. Remember, I squared is negative 1, I cubed was negative I to the 4th is 1, and so on. Right? I shouldn't have to go into that. But you plug in all three of these, you would get 0. And if you were to plug in 1, the output should be 10. And it would be, I can see that right here. Great. Yeah, so it was really that simple. I mean, it's just like, again, I've done this before, but where all the zeros were real. The only difference here is you're given a zeros with some imaginary number in it. You just have to remember that the conjugate would also be a 0, and then it's basically the same thing. Great. Alright, so I'm hoping that watching me go over just these couple examples here helps you when you're asked to, write a polynomial function given certain zeros, and it's a polynomial function with real coefficients, so the complex conjugate theorem should apply. You got to keep that in mind. And yeah, I'm hoping this helps you when you do that on your own. And thank you very much for watching.